Hello guys, welcome to Amazing Engineering, and today in this MatLab tutorial we will see the forward and inverse kinematic analysis of a robot and its trajectory. As first, we have to define the robot using the Denavit and Hartenberg parameters in a standard or modified configuration as we did in the previous video. So, let's define a robot variable using the command serial link. And now we can start with the forward kinematic analysis. In this case, we want to define the configuration matrix of the end effector using the joint variables vector of the robot in a certain configuration. So let's define the vector, for example QF. In this case, we are using a robot made up by 5 rotary joints. So we can write, for example, half p minus p6 minus p quarter, half p and 0. Now we can define the matrix called, for example, TF, using the fkin command, so the forward kinematic command. Let's write kr, so the robot variable point fkin, and we use the qf vector we have just defined. Let's run the simulation. As you can see, TF is an SE3 matrix, so an homogeneous matrix defined in the space, and we can see its component in the common window, and we can see a rotation submatrix and a translation submatrix. Now we can use the same matrix in order to define the inverse kinematic analysis, where we want to define the joint variables vector of the robot in a certain configuration of the end effector. As first, we have to define the Q0 vector, the joint variables vector in the initial configuration of the robot. For example, if we use the rest position of the robot, all the variables are equal to 0. Then we can find the joint variables vector in a certain using the TF matrix of the end effector using the ikin command, so the inverse kinematic command. Let's write kr point ikin. We have to use the TF matrix, the joint variables vector in the initial position, and now we have to define the max vector. This vector is made up by 1 row and 6 columns, and its components are equal to the logical values 1 or 0. The 6 columns represent the 6 degrees of freedom of a body in the space, and the logical values are used to define the number of degrees of freedom of the robot. For example, if we are using a 6 degrees of freedom robot, all the components are equal to 1. In this case, we are using a 5 degrees of freedom robot, so the first components of the vector are equal to 1, and the last one is equal to 0. So, using the logical value 1, we are saying that the degree of freedom is true. Instead, using the 0 logical value, we are saying that the degree of freedom is equal to false. Let's run the simulation. Now, if we see the Q components in the common window, and we see that they are similar to the component of QF vector we defined before. Sometimes you can see a warning message in the command window which means that MATLAB made an error in the inverse kinematic analysis. However, it is a very little error, something like 10 to the minus 12 or something else. Now the last aspect we want to analyze is the trajectory of the robot. As first, we have to define a time interval which, for example, moves from 0 to 3 seconds with a time step of 0.15, and if we use the jtrace command, we can define the matrix called Q, whose components are equal to the joint variables calculated in each time interval. We have to use the joint variables vector in the initial and the final position of the trajectory and the time vector. Let's run the simulation again. As you can see, Q is made up by 21 rows because we are using 21 time interval, and 5 columns equal to the number of joints which make up the robot. Now, if we use the Q matrix in the fkin command, like this, we can define a series of configuration metrics on the end effector calculated in each time interval. So TR is made up by several configuration metrics on the end effector. In order to represent the trajectory of the robot, we have to define a for cycle using a variable which moves from 1 to the length of the time vector with an increment equal to 1. Let's define t variable, which is equal to the matrix of the tr variable respect a certain interval. For example, during the first cycle, I is equal to 1, so t is equal to the first matrix of tr. In the second cycle, I is equal to 2, so t is equal to the second matrix of tr, and so on. Now let's extract the translation component of the t matrix using the command transl. Now we have to define the coordinates vector of the trajectory using the first, second, and third component of the vector trs. So the x coordinates vector is equal to the first component of the vector trs. The y coordinates vector is equal to the second component of trs, and the z coordinates vector is equal to the third component of the vector trs. We can close the for cycle. Now if we plot kr and the Q matrix, we can represent the motion of the robot, and if we want to represent the trajectory of the robot, let's write hold on in order to keep the plot window opened. Let's use the command plot3 because we are plotting a curve in the space. Let's use the coordinates vector of the trajectory. Let's define the color using this vector, If we write 1, 0, 0, the color is red, 0, 1, 0, the color is green, and 0, 0, 1, the color is blue. Then let's write line width, which means that we are using a line, and at the end we have to define the line thickness, for example 2. Let's run the simulation. So this is the robot motion, and this is the trajectory. Well, this is all for today. I invite you to subscribe on my channel and see you for the next video.